Let's talk about section 3.6, the chain rule. Here's our definition. dy dx can be thought of as the product of dy du times du dx. Now, please note that could be anything like dy dx is also equal to dy d v times dv dx. In other words, what's important is that these two things are both the same. They seemingly cancel, forming the dy dx. Okay, so it looks like a fraction, kind of acts like a fraction. So let's just say that's where we're at, right? So let's take a look at how the big implication of this particular rule. It says if you have y is equal to 6x minus 10, find dy dx. Well, that's pretty easy to do. We'll take the derivative with respect to x of both sides of that equation. Okay, and we get dy dx, and derivative of 6x is 6, and derivative of negative 10, it's a constant, so it's a 0, so it's equal to 6. You're like, wow, that was not hard. What does that have to do with the chain rule? Well, let's recognize that this equation is the equivalent of saying y is equal to 2u if u is equal to 3x minus 5. Again, imagine y is equal to 2 times u, and u is 3x minus 5. And you can see that we get exactly that. Okay, can we find the derivative using the chain rule now? Okay, well, what would we have to do? Well, first we'll have to find dy du. So here's y and 2u, right? I'm going to take the derivative with respect to x of both sides of the equation. I'm sorry, the derivative with respect to u of both sides of the equation. And I get dy du is equal to 2. Great. Now we're going to take u is equal to 3x minus 5, and let's take the derivative of both sides of that with respect to x. This gets us du dx is equal to 3. Great. So what is dy dx? Well, again, it's dy du times du dx, which is 2 times 3, which is 6. And that exactly matches the other one. You're like, why are we doing this? It was so much easier to do it this way, and we get the same answer. And I'm going to say you're absolutely right. We get exactly the same answer, and it's hard to justify using the chain rule in that circumstance. But let me make an argument that as things get more complicated, we might want to, again, think about how the chain rule might be helpful. Take a look at this polynomial. 9x to the fourth plus 6x squared plus 1. And if we just did the dy dx, we'd end up getting what? 9 times 4 is 36x cubed plus 12x, if we had it this way. But imagine instead the problem was presented this way. And you're like, well, what I don't want to do is I don't want to have to expand that. Could we use the chain rule instead? Could we think of this expression, 3x squared plus 1, quantity squared, as being two functions, u squared, where u is equal to 3x squared minus 1. Can we think of that problem in that way? Well, let's give it a try. So if we take the derivative of the first equation with respect to u, we get dy du is equal to 2u. If we take the second equation with respect to x, squared plus 1, we get du dx is equal to 6x. So if I ask what is dy dx, you say, well, it's dy du times du dx, which is equal to 2u times 6x. But I don't like that u being in there. Perhaps I really should think of this as 2 times u, and u is 3x plus 1 times 6x. Now, here's where I want to recognize that if we did expand this, I get 6x squared plus 2 times 6x, which is 36x cubed plus 12x. And we get the same thing there. Okay. But I want to look at this particular writing of it. What do we have here? This 6x is coming from the derivative of that. I'm going to call that the inside function. Why? Because that u is being operated on by the squared. Where did this 2 come from? From the derivative of u squared, 2u. So oftentimes, and actually more often than using the chain rules that originally stated, we are going to think about using this chain rule whenever we encounter a composite function, a function with another function inside of it. And the chain rule in this instance says, you want to find the derivative of that composite function? Take the derivative of the outside function and leave the inside function the same. That is what we have right here when we say the 2 times the 3x cubed plus 1. We took the derivative of the outside, that gives us the 2u, and then we put u unadulterated back into u. Or the expression is equal to u back into that expression. Derivative of the outside, leave the inside the same. Then multiply that by the derivative of the inside function. Like that 6x is going on there. All right? So my mantra for this particular kind of problem is going to be derivative of the outside, leave the inside the same, multiply by the derivative of the inside. Let's take a look at this in action. As an object moves, so its position at any time greater than 0 is given by cosine t squared plus 1. Find the velocity of the object as a function of t. All right, so I'm going to take x of t, and I'm going to take the derivative with respect to t. I'm going to take the derivative of position with respect to time. All right? And when I take the derivative of position with respect to time, I can think of this as dx dt, but I could also think of this as velocity. Now, the derivative of this side, I want you to see that cosine is the outside function, and t squared plus 1 is the inside function. So if I do the mantra for the chain rule, I say the derivative of the outside, which is negative sine, but I leave the inside function the same. But then I close this out by multiplying by the derivative of the inside function, which in this case is 2t. Now, you may clean that up, put that negative and then the 2t out in front, and then call this sine of t squared plus 1. That'd be a way to rewrite that a little bit more cleanly. Right? So, again, one more time, the mantra, differentiate the outside function, leave the inside function the same, and then multiply by the derivative of the inside function. Let's try this one more time with another derivative. A derivative with respect to t of gt, derivative with respect to t of tangent of 5 minus sine, This has got a lot going on here. So I know that I can call this G prime on that side. The outside function is the tan function. The inside function is all that stuff inside the parenthesis. So when I take that derivative, I'm saying, well, what's the derivative of tan? Well, from the earlier lesson, we learned that that is secant squared. What do? I leave this all the same, leave the inside the same. And then I follow this up with, what is the derivative of the inside? What is the derivative of 5 minus sine of 2? Well, the derivative of 5 is 0. I'm not even going to write it. Negative, the derivative of sine is cosine. Oh, wait, the derivative of cosine of sine 2t, that in itself is a composite function. Derivative of the outside, cosine, leave the inside the same. And what do? Follow that up with the derivative of the inside. And again, maybe we clean that up a little bit. Negative 2 secant squared 5 minus sine of 2t times cosine 2t. And there's a perfectly legitimate answer. All right. Now, you may recall doing in pre-calculus something called parametric equations. In a parametric equation, we have x as a function of t. We have y as a function of t, and then the curve is described as t. The parameter changes. It describes the curve as x and y change. This these parametric equations can describe curves that we can't describe normally using single variables, like y as a function of x. But we'll take a look and see what happens. Big idea though is you want to find the slope of a parametric equation. Here's our formula: dy dt over dx dt. Wait, let me rewrite that in a slightly different way. Dy dt divided by, which is like multiplying by the reciprocal, dt dx. Oh, look at that. The dt's cancel. It's just another application of the chain rule. All right, so here we go. Find the line tangent to the right-hand hyperbola branch as defined parametrically as these two curves. Okay, great. Let's take a look at the elements of what we need. We need dy dt. Well, here's y. So let me take the derivative with respect to t of both sides of that equation. And I get dy dt is equal to secant squared t. Let's take the derivative with respect to t of the x equation. Taking the derivative of both sides, this is secant. So this is dx dt, and the derivative of secant is secant t tangent t. So what is dy dx, the slope of the tangent curve? It's going to be secant squared t over secant t tangent t. And if you're into cleaning up, this turns into secant over tangent. And I think we could just, that should be a t there. I think that's fine. So what's the slope that we're looking for? What is dy dt when t is pi over 4? Well, that would be the secant of pi over 4 divided by the tangent of pi over 4. Well, the tangent of pi over 4 is 1. We know that. Secant of pi over 4, I think, is root 2. All right? So I think the slope is root 2, and we're given a point. So our tangent line will be y equals y1. There's y1, it's 1, plus root 2, the slope, times x minus root 2. Well, let's see if indeed graphically this looks correct. I've got my calculator handy. I'm going to go to graphing mode. I'm going to go to menu and go to option 3 and change this over to a parametric graphing mode. I think we said that the x value is secant of t. Double check. Yep. And y is tangent of t. And if I hit enter, we get this curvy thing. I'm going to take my calculator. I'm going to switch it back to function mode. I'm going to go ahead and put in the equation that we said was the tangent line. This was what? X. Is this right? X minus root 2. Okay. X minus root 2. All right. I hit enter. All right. And does it look like the big thick blue line is tangent to the thin blue line? It does to me. All right. So those parametric curves, again, they move as the value of t's change, and we can still find tangent lines. All right, let's go ahead and do these other examples. Find the slope of the line tangent to the curve sine of x, sine to the fifth x at that particular location. All right, so let's take the derivative with respect to x of both sides of that equation. And I really hate this notation because it makes it difficult to see what's the outside function, which is the sine is the inside, and to the fifth is the outside function. So once I do that, maybe it's easier to see that the derivative is derivative of the outside, something to the fifth. So we use the power rule, bring the 5 down, keep the inside the same, reduce the power because that's part of taking the derivative of the outside, and then multiply this by the derivative of the inside, which is cosine. So this is what dy dx is equal to 5 sine to the fourth x, right? And then the question is, well, what's that slope when we're at x is pi over 3? So what is 5? And again, I think it's easier to see what we're doing if we keep that 4 to the outside and cosine pi over 3. We should have memorized the sine of pi over 3. I believe the sine of pi over 3 is root 3 over 2, which I'm going to take to the fourth power, and the cosine of pi over 3, which I think is 1/2. So if we do a little bit of cleaning up, it looks like I have 2 to the 5th in the denominator, 2 to the 5th. I think that's 32. And then on the numerator, I got 5 times 9, which is 45. At least that's what I think it is. All right, one more. Okay. Show that the slope of every tangent line to this curve is positive. Now, you may be thinking, that looks like a fraction, I could use the quotient rule. And you would be right. But maybe, just maybe, it's easier to do this problem if we think of it as a composite function. Since there's only a constant in the top, how about we just say this is equivalent to 1 minus 2x to the negative third power. And then I'll take the derivative with root of both sides with respect to x. And I get dy dx is equal to, bring the negative 3 down, keep the inside the same, reduce the power by 1, which is negative 4, because getting smaller makes it more negative. And then we multiply that by the derivative of the inside, which in this case is negative 2. If I clean that up, I get positive 6 over x minus, or 1 minus x, 2x to the fourth power. My claim is that indeed that is greater than 0, because 6 is positive, and 1 minus 2x to the fourth power, an even power, that's also positive. So when you divide two positive numbers, two positive numbers, divide a positive number by positive, you get a positive number. Now there is an argument to say, well, what about when this is equal to 0? What about when we're at 1/2? What's going on there? Well, at x equals 1/2, there is no slope. Slope doesn't exist. So I don't have to worry about it being positive. It just says the slope, which means it has to exist, has to be positive. There we go. All right. And that concludes our discussion of section 3.6.